So, good afternoon and welcome back to the afternoon sessions of the day on Terahertz detectors and sources, along with Terahertz radiation and elementary excitation by Dr. V. Nagarajan. To begin with, I would like to introduce the speaker of this session. Dr. V. Nagarajan is a professor with the Department of Electronics Engineering, Pondicherry University. He received his master's degree in Electronics and Communication Engineering and his doctorate in Wireless Communication from Pondicherry Engineering College, Pondicherry University. He has 2 decades plus research and academic experience and has held various research and academic positions. His research areas of interest include wireless communication, signal processing, IoT, machine learning application to wireless communication, and sensor networks. He has co-authored 6 books and 200 plus research publications and book chapters. He is the founding chair of IEEE Technically Co-Sponsored Conference ICCSP, which completed 9 successful editions. He is a student project subcommittee chairman and member of the Communication Society as well as a senior member of IEEE and fellow of IETE. He has served as an associate editor and has guest edited 6 special issues in Elsevier Journal on the computer and electrical engineering. He has successfully graduated with 24 PhDs. Furthermore, he has completed several research projects funded by DST, IEEE, and TNSC. We are happy to have you, sir. Over to you now.
Good afternoon to all. Thank you for that introduction. I hope all of the participants are familiar with Terahertz communication. I think the slides are visible now.
Yes, sir. It's visible, sir.
Yes. Good. Uh, Terahertz radiation and elementary. So the first actually today I have a couple of sections. One is Terahertz radiation and elementary stations. Another one is source and directors. So in first topic, schedule terahertz radiation and elementary excitation, what it means, terahertz radiation and elementary excitation, that the history and need for this terahertz radiations. See here that introduction of the terahertz radiation and elementary radiations means terahertz radiation refers to electromagnetic waves in the frequency range of 0.1 to 10 terahertz, or we can say that in wavelength between 3 mm and 30 micrometer. So it lies between microwave and infrared regions in the electromagnetic spectrums. So they have that electromagnetic spectrums in between that some portions are not investigated. Not investigated means properly it lies because of the that the source and director is making it a complicated process. So that's why they didn't concentrate on this terahertz. And now that technologies are coming out, no? So now it is easy to easy for choosing that source and director. So it plays that terahertz plays that important resource in this sixth generation systems. So element is here that elementary excitations refer to quasi-particles and collective modes in condensed matter systems that describe fundamental interactions such as phonons, mesons, plasmons, and exons. These excitations play a crucial role in understanding quantum materials, superconductors, and nanotechnology. These are the general space of terahertz. So this is the frequency range of terahertz radiations occupy the spectrum from 0.1 to 10 terahertz. Wavelength from 30 micrometers to 3 millimeters. The property could be non-ionizing, safe for biological tissues and high penetrations. It can capable of penetrating paper, fabrics, plastics, and ceramics. So it has that low energy position between microwave and infrared regions. Mainly, the application focus on imaging, which consists of not invasive imaging for security screening. For example, we are using for airport scanner because before previously they used the X-ray systems, uh, which was not maintaining the privacy of the passengers. But here, because of that non-invasive imaging for security screening, that all passengers are liking this terahertz radiation schemes. And spectroscopy, studying material absorption, emission spectrum for chemical identification. In communication, ultra high-speed wireless communication system, we are using that. In medical, it is used to detect that cancer detection, wound monitoring, and non-invasive diagnostics. Is it the slides are visible now? Anyone?
Yes, sir, it's
Ah,
visible.
yes, yes, okay. So this history of terahertz radiation and elementary excitations, that the early development in terahertz science include in late 19th century theoretical predictions of terahertz waves as part of the electromagnetic spectrums were made by I think Maxwell. Okay, during the 1900 to 1930s, mostly that experienced by Hertz and Bose demonstrated wave propagation at millimeter. Mostly we are using in the fifth generation communication system, also millimeter and sub-millimeter wavelength, but generating and directing terror waves remained a challenge. That's why that they didn't focus on terahertz. Now easy to generate, and that the challenging processes are before that complicated. Now made they made very easy for generating that terahertz sources. That's why more research are going on this topic. So earlier, 1970s, 1980, very that is interest in for infrared spectroscopy led to advances in Fourier transform, infrared spectroscopy, and black body radiation sources. But the terahertz was still inefficient during the 1980s. Okay, in 1990s, the invention of terahertz time domain spectroscopy enabled real-time terahertz wave detection and revolutionizing terahertz research. So this historical development of elementary excitation started with that during 1920s. The concept of quasi particles was introduced by Live, laying the foundation for elementary excitation in quantum systems during the 1930s and I think 1950. Phonons were described as quantized lattice vibrations, and plasmons were proposed by Bohm, and magnons were studied in ferromagnetics. And during 19th research expanded into strongly correlated electron system, superconductors, and low dimensional materials like it.
So sorry for disturbing, sir.
Ah,
Actually,
ah,
the slides are not moving.
okay, okay, okay. Right. Yes. Okay. See, actually, generation and direction of terahertz Phot- photoconductive antennas and optical rectification, quantum cascade lasers, frequency multipliers, and the plasma-based methods. These are the generation techniques available for that terahertz. And direction techniques are electro-optic assembling, photoconductive assembling, polometers, and circuit heads. These are the things. These are the techniques available. Just generally that how that waves are interacting with the materials. That is the concept. How? So then only we can easily recognize what are the things are going on in the scenario. So, for example, so before that, we know that about electromagnetics waves. So, electromagnetic waves by using that Maxwell equation. Okay. So, Maxwell equation, we know that how it travels and what are the things are happening in that any material when electromagnet is impinging. Okay, so the similar things because that this is a electromagnetic spectrum. This is a electromagnetic spectrum. In between, we are concentrating on and this one 0.1 to 10 terahertz regions. Okay, this is the electromagnetic spectrum. In between this wavelength between microwave and infrared regions. These frequencies offering that good throughput, that is high throughput. Okay, so for high speed communication we can use this band because sixth generation expect that terabits per second communication. So 5G is offering that gigabits per second, and 4G offers that megabits per second. megabits per second communication. So here it offers that high throughput, but only that the problem is multipath. That is the three phase path loss. Sorry, path loss. So path loss we are expecting. We are mitigating this path loss. We can enjoy the benefit of the terahertz. Okay, this point 1 to 10 terahertz regions. So here the interaction of terahertz radiation with matter. So we know that terahertz offers that good uh, output. Okay, terahertz. In this region, we can expect that high speed communication. It offers that high throughput also we can expect. Okay, speedy. So that only is path and source and detector is complicated. That's why that during that 1970 and during that 1920 they didn't concentrate much about this. Okay, so now the technology is improved, so we are having that numerous advantage over these terahertz. So why can't we use it? Use this for generating and detecting principle we are implementing. We can easily utilize the advantage of terahertz. Fields. So here, so we should know about that interaction of terahertz. So previous slide. So actually here first slide these are the range wavelength from the 30 micrometer to 3 mm we are seeing it. So these are the sources because that generating technique and detection is very complicated process in the complicated process. That's why it is not familiar. Okay, now it is somewhat easy to generate. Not easy to generate, but we can generate. So the sources are available. Now we have to know about the exudations. Okay, how that radiation and elementary exudations, modern science. We have to know. So see, older peoples are there, new peoples are there. So that the new people don't know about that old people. Okay, that because traditionally they have utilized some protocol, so many things. If that new fellows or that modern criteria fellows are not following that traditional methods. If we are we are following the traditional method, it gives that numerous advantage and growth. No, so here also that similar things only. So we have to know about the terahertz, how it reacts in the matters. So interaction of terahertz radiation with matter. That is the topic we are going to discuss about this for 1 hour lecture camp, 1 to 1.5 hour lecture camp. So here that absorptions and transmissions and scattering and reflections. So generally that waves experiencing that scattering, reflections, observations. Okay, so terahertz radiations is absorbed by water, which makes it effective for detecting moisture content. So by using these properties, okay, terahertz radiation is the methods. By means of that observation property, yeah, but it easily detects that moisture content. And by using the transmission property, it vary across different materials, enabling imaging and spectroscopy applications. Okay, so and the scattering and reflection, scattering effects can be exploited to image subsurface defects in non-ionizing metallic materials, and the reflection-based imaging is useful for surface analysis in material science. So this absorption, scattering, reflection scatters we are using, and we are experiencing the application of this terahertz. Okay, so this is the elementary exaggeration material. So before that, some of the point I have to focus here. Why is study that terahertz radiation? Terahertz radiation and why study of elementary exaggeration? So that is important. Why study of terahertz radiation and why study of elementary exaggeration? We know that elementary exaggeration in material, elementary exaggeration refer to quantized collective phenomena in materials that describe how systems respond to expansibility such as electromagnetic fields. Suppose how we can say this fellow is having the capability of leading the team. Okay, so all can lead the team. How efficiently that fellow is leading the team? So many fellows are there. So many guys are there. But out of that guys, one fellow is known as a captain. Why we are saying he is a captain? The decision making capability. Okay, decision making ability. How efficiently he can take the decision. Based upon this only, we can say that he is a good leader. Okay, so how taking the decision, his characters, how he reacts. Based upon that individual person characters, we can decide he is eligible. So here, the terrorists fields are there, no? These fields by passing, okay, in material, it passing to materials, it passing to materials. Now, how it reacts, we have to know. We have to know the characteristics. Based upon this, we can choose that applications because that fellow, suppose any fellows are done. Morning time, if we meet that fellow, he will get tension. Okay, afternoon he will be relaxed. Evening time he will be good day. So based upon that time period, also one mood will change. Okay, isn't it? So like this here also, we are concentrating on that Terahertz wave, how it reacts in the materials. Okay, types of elementary excitation. What are the elementary excitations available? We are going to see. Before that, the study of radiation and elementary excitation. Non-ionizing safe for imaging. Unlike X-rays, see already I mentioned that more and most advantage of terahertz waves are unlike X-rays. Terahertz waves don't ionize biological tissues. Okay, it doesn't ionize biological tissues, making them ideal for biomedical imaging and security screening. Because if you are going to airport. And before that X-ray scanning was available. Okay, and also some airports it is available. The whole body it used to scan because non-medico is seeing that structures. It is not good. If a medical person is seeing that is different. Okay, so not maintaining that privacy of that passengers. That's why all are liking these terahertz waves. Because of this ionized biological tissues, then ideal for biomedical imaging and security system. These terahertz do not ionize. Okay, so terahertz waves do not, but X-ray waves are ionized in biological tissues. So this is the greatest advantage for that biomedical imaging application. And one more thing is spectroscopic fingerprinting. Terahertz can probe unique vibrational and rotational modes of molecules useful in chemical sensing and paramedicals. Okay, paramedicals. And one more thing is this radiations we can use for high-speed wireless communication because that frequency range is zero point 0.1 to 10 terahertz, key for 6G networks, enabling terabit per second data transfer. In 5G, it offers the giga bits per second. And one more, the study of terahertz radiation is essential for material science and semiconductor research, which reveals carrier dynamics in semiconductor, superconductor, and quantum materials. These are the main contributions and the main applications relevant to the terahertz radiations. This elementary excitation is in materials. Okay, so here how it reacts in that material. So based upon this, we can choose that applications depend upon that materials also. Why study of elementary? What is the need? Why study? We study that elementary excitations. So, for example, that uh, quantum materials, excitation like see here excitations like phonons, excidons, and the plasmons determine the fundamental properties of topological insulators, superconductors, and 2D materials. Okay, so that's why that we are studying for that elementary excitation. The need for the study for elementary excitation depend upon. Okay, excitation like phonons, exidons, and plasmons determine the fundamental property of topological insulators, high superconductor, and 2D materials, and nanoelectronics and spintronics, magnons, and which enables next generation low power computing and memory devices. And next also that the energy transport and superconductivity govern heat transport and play a crucial role in unconventional superconductivities and terahertz spectroscopy application. Terahertz pulses can directly excite and probe elementary excitation, offering a new window into quantum phase transitions and ultra-fast dynamics. So, the Terahertz radiation and the elementary excitations are at the frontier of modern physics and technology, where the applications span wireless communication and bioimaging and ultrafast sciences. So this terahertz radiations with these frequencies between the microwave and infrared has gained attention due to the application of various sources. So here we are going to concentrate on these types of elementary exhibitions. What are this? And mathematically we are going to see what are the things are happening in this system. So here, these types of elementary exhibition. Voice are audible? Is it voice is audible?
Yes, sir, it's audible.
Okay. Types of elementary exist. Phonons. A phonon is a quantized mode of vibration occurring in a rigid crystal that is representing the collective vibration of atoms. So it is used to indicate that vibration of atoms. Phonons play a key role in thermal conductivity and lattice dynamics. See, the phonons play a key role in various areas of material science and technology. So, for example, in thermal conductivities, phonons are the primary carriers of heat in non-metallic solids, which understand phenon behavior helps improve the thermoelectric material. And that superconductivities, phonon mitigate electron pairing in conventional superconductors by following the BCS theory. And phononic crystals, these materials manipulate phonon propagations for thermal insulation or wave guiding applications. And acoustic devices. Phonon-based technologies are used in surface acoustic devices for communication and sensing. These are the where that phonons play a key role in various areas of material science technologies. Here, these phonon and radiations, phonon and terahertz radiation, that mathematically we can study about the reactions of that phonon. So phonon interacts strongly with the terahertz radiation due to their vibration because it has that vibrational frequencies being in the terahertz range. So it has that vibration frequencies in the terahertz range. Okay, terahertz range. It is that 0.1 to 10 terahertz range. This equation indicates that phonon dispersion relations. Omega q equal to root of c by m sine QA by 2. So here, this is the phonon frequency. What is the frequency range? And c is the force constant, and m is the atomic mass, and q is the wave vector, and a is the lattice constant. Okay. So by using this, we can easily calculate that dispersions relations and the absorptions of the cross sections indicate alpha omega by epsilon naught dou e by dou a. Here, the terahertz absorption because based upon that reflection, scattering. So this property we are concentrating on, and this is absorption. So absorption, scattering, and reflections. Okay. So how we can say that that a fellow is capable of guiding that entire team based upon his characters. Okay. So during that critical situation, how it reacts. Okay. During that enjoyment period, how it reacts, how he give respect to that elder persons. Based upon this, we can easily says that person is capable to handling that any situations. Like this here, also we are analyzing the situations of that and that is these waves. Okay, that these radiations. This radiation is absorbed by water, which makes it effective for detecting moisture content. Okay, these properties, absorption, scattering, and reflections. So here, absorption cache sections, terahertz absorption is governed by the phonon absorption coefficients. Okay, so here that is epsilon is the dielectric constants of the structures, and epsilon naught is the vacuum permittivity. Okay, permittivity based upon that material what we are using that one. And here the angular frequency of the phonon as a function of the wave vector and the spring constant force that represent the restoring force between adjacent atom and the lattice, and m the mass of each atom in the lattice, and the wave vector of the phonon related to the wavelength by q equal to 2 pi by lambda. So A is nothing but the lattice constant, which is the distance between adjacent atom in the crystals. Okay, that's crystals we are studying, uh, and this by using the mathematical representation, it gives that correct pictures. So what from these equations we picture out now physical interpretations. That is Conan vibration in a one-dimensional crystal. Atoms are connected by springs that is modeled as harmonic oscillators. When the atoms vibrate collectively, the vibration propagates at wave. This quantized wave is not phonons. Okay. When the atoms vibrate collectively, the vibration propagates at waves, and these quantized vibrations are called photons. This is the interpretations we obtained from this. And the sinusoidal dependence, the sign term describes how the frequency depend on the wave vector q. The highest frequency achieved when q equal to by a. This corresponds to the brilliant zone boundary behind which the wave are pulled back due to the periodicity. This the sign, okay, this sign indicates. So phonon dispersion relations. Okay, how the phonon interacts strongly with Terahertz radiation due to the vibrational frequency being the Terahertz range. These phonon dispersion relations, these equations state that omega q state that one-dimensional crystal atoms are connected by springs. When the atoms vibrate collectively, the vibration propagates waves, and these quantized vibrations are called phonons. Okay. So this q, that the small wave vectors, the sign function behaves approximately as sin equal to q by 2, approximately 2 by 8, leading to omega q equal to root of c by m q a by 2. This linear relationship indicates acoustic phonon modes where the frequency is proportional to the wave vector, similar to sound waves. Okay, this one indicates the high Q behavior. This one, see, when low Q behavior, when small behavior, this relationship indicates acoustic phenomenon modes. The frequency is proportional to the wave vector, similar to sound waves. When Q behavior, high Q behavior, okay, approaches the zone boundary, the frequency saturates as corresponding to optical phonon modes in more complex lattice or maximum vibration frequency in a simple lattice. Okay, Q behavior determines. Okay, this Q behavior determines frequencies proportional to the wave vector, similar to the sound waves. When high Q behavior indicates which approaches the zone boundary, frequency saturates corresponding to optimal phonon modes, which are more complex lattice, maximum vibrational frequency in a simple lattice system. So this one indicates the such behavior of the phonon. So where we are using this for means thermal conductivity, mostly the phonon dispersion relation is this dispersion where we are using this dispersion relation because it gives that omega q approaches at root by c by m q a na q a by 2. This q low q behavior na proportional to the wave vector, and high q behavior means maximum vibrational frequency in simple lattice it indicates. So where this dispersion relation is essential na, for understanding how heat is transported in solid. Okay, how heat is transported in the solid. This dispersion delts, okay, indicates, okay, what are the things the phonon dispersion relations delts for understanding how heat is transported in the solids. And Terahertz spectroscopy. This Terahertz radiation can probe phenomenon mode. So radiation in phonon mode na. So that fellow, for one fellow is having that typical situation na. For example, you can say that one fellow handles that only he performs the toughest situations only. So you can say that a cricketer and some fellows hit like that Dhoni used to hit sixer in the last over only 6 balls. Okay. So here the Terahertz radiation can probe phonon modes allowing analysis of crystal structure and lattice vibration. Okay, that is important. Because of this uh, phonon modes, which analyzes crystal structures and lattice vibrations. And phonon behavior plays a critical role in convention because, for example, you can say that before 1 month before you are having you have to write that examination, you are going for any interview. During the 10 days, 20 days could be there. Before that, some 20-30% of student or students will try to cover the syllabus. But most of the members used to cover the syllabus, take the book before the examination only. Before the examination only, or 2 or 3 days before only they used to take. Okay, so actually during that situations, okay, during the situations that everything will be active. Okay, so here in this mode, this phonon mode only allowing analysis of crystal structures and lattice vibrations. Okay, can probe phonon mode. Terahertz edition can probe phonon mode allowing analysis of crystal structures and lattice vibrations, and phonon behavior plays a critical role in conventional superconductors. Okay, there where we can use it. So here up to now we have discussed that elementary excitation in material. Okay, terahertz offering that more advantage. We know that. Okay, so what is the need for studying elementary excitations? Okay, elementary excitations in material. Excitation like phonons, excions, plasmons determine the fundamental property of insulators, superconductors, and 2D materials. That's why we are concentrating about these elementary excitations. Okay, so phonons we have studied, we have uh, discussed about the phonon and the terahertz radiations by using this equations and the discussions. Uh, yes, this dispersion relation, these mathematical dispersion relations, we are understanding how it is transferred to the solid. Okay, so next, these are the see here alpha omega, the observation coefficient which represents how much terahertz or any electromagnetic radiation is observed per unit distance that is propagation through the medium. Okay, alpha omega. Omega, the angular frequency of the incident radiation, and epsilon naught, the atom permittivity, a constant that relates electric field to the electric field in free phase, and epsilon omega, the the dielectric constant of the metal, which can vary with frequency. The dielectric constant epsilon omega characterize how the medium responds to an applied electric field. That is very important. The medium experiencing. So that difficult situations one fellow is facing, he will be molded. Some fellow will be depressed. Okay, so even though the persons is getting more problem, he will be more confident. He will be getting that more confident. Some fellows facing that more problem, he will be depressed. So like this here also, that the materials, okay, characters how the medium respond to that applied electric field. So dou say epsilon by dou omega, the rate of change of the dielectric constant. So dielectric constants with respect to frequencies. Okay, change of dielectric constant. The term reflects how the material ability to polarize change with the frequencies, how the materials reacts. Okay, so this mathematically, this mathematically expresses that what are the things are going on. Okay, so that physical interpretations, the term d omega yes, uh, indicates the frequency dependent behavior of the materials polarization driven by the electromagnetic field. A high D suggests strong dispersions, rapid change in the dielectric constant with frequency, which is often associated with the resonant absorption, like phonon or plasmon resonances, and that the proportionality of omega by epsilon naught highlight the fact that higher frequency radiation typically results in stronger absorption due to increased interaction with the dipole oscillations or chain carriers in the materials. Okay, these interpretations we are getting from this method. Mainly these applications, Terahertz spectroscopy, material characterization, and resonant observations. By using this expression is used to model how much absorbed in this Terahertz spectroscopy, especially for analyzing materials with the strong. So how we can evaluate that students rank based upon their uh, internal exam and based upon that main exam marks. Based upon that marks, we can highlight their rank. So this is the usual procedure. Okay, like this here also that this model absorption terahertz spectroscopy actually for analyzing material with strong phonon or extron resonance and material characterization, the big area of alpha omega with respect to omega and epsilon omega helps identify material properties such as electronic transitions, vibration modes of or charge carrier densities, okay, and resonance observations. Near resonance frequencies, because the Terahertz frequencies that reflection and scattering is the reflection and scattering. In this property is giving that good output for analyzing that Terahertz, that material details. Okay, so near resonant frequencies, for example, that phonon or plasmon mode, the absorption coefficient will show peaks, providing insight into the nature of the material's resonant exhalations. Okay, next one is plasmons. Okay, that elementary exhalations. So many elements are available. So first one we had seen about phonons, and this one is plasmons. The slides are visible.
Yes, sir, it's visible, sir.
Plasmons. So so we know that collective oscillation of free electron clouds, particularly in metals and semiconductors. Surface plasmon polarization of surface tone waves coupled to the Terahertz fields. So plasmons are using variety of cutting edge technologies. Okay, this plasmons enhances light matters interactions, leading to high efficiency photonic circuit and optical chips. And plasmons amplify Raman scattering signals following ultra-sensitive chemical and biologic sensing. These are the characters of plasmons. And plasmonic nanoparticles are integrated into solar cells to enhance light absorptions. And plasmon-based sensors such as surface plasmon resonance are used for real-time detection of biomolecules. So this one, plasmon coupled with Terahertz addition due to the oscillation of free electrons at terahertz frequency. This is plasmons coupled with terahertz radiation due to the oscillation. This is the important oscillation of free electrons, oscillation of the free electrons at terahertz frequencies. Okay, so how this plasmon frequency? Omega p equal to root of n square epsilon naught m star. So here that n is the free electron density and E is the electron charge. M star is the effective mass and epsilon naught is the vacuum permittivity. Okay, so here epsilon omega dielectric functions terahertz region. The dielectric function for plasmon terahertz interaction epsilon omega equal to epsilon infinity to 1 minus omega of c square omega square plus I gamma omega. Here epsilon infinity is the high frequency dielectric constant and C is the damping constant. So next one is magnon. Okay, magnon. So this magnon is a quantized spin wave representing the collective excitation of electron spins in a magnetically ordered material. So it is used to give that how that electron spins in that magnetic material. The study of it is useful for magnets are critical in the study of magnetism and spintronics. So this magnon transport is being explored as a way to transport information using thin waves, offering energy efficient alternatives to electronic charge transport. and it is central to the development of magnetic materials and spin-based devices. Magnetochloric effect are key in magnetic refrigeration technologies, and ferrite materials that exhibit magneton excitations are used in microwave communication devices and quantum information. Magneton qubits are being export for quantum computing applications. So, these nanoelectronics and spintronics, magnons and skyromints are enable next generation low power computing and memory devices. Okay, memory devices. So this magnon and terahertz radiation, these spin waves typically have frequencies in the gigahertz to terahertz range, making them relevant to terahertz interactions. Okay, so this one is important for that. Magnons means spin waves typically have frequencies in this range and relevant to the terahertz interactions, which represent the dispersions. Dispersion relations indicates omega k equal to h plus d k square, where omega k is the Magnon frequency, gamma is the barometric ratio. This is h is the applied magnetic field, d is the spin stiffness constant, and k is the wave vectors. So here, this is the dispersion relations and the terahertz observation alpha omega. This terahertz observation cross section for magnons depends on spin lattice coupling and is modeled by this one. Okay, that's why omega is the magnetic sensibility. Okay. Here omega k, the angular frequency of the magneton, has a function of the wave vector k, and h, the applied magnetic field. The term represents the Zeeman energy contribution, which causes the precession of magnetic moments under external field. D is nothing but the change stiffness constant, which describes the strength of exchange interaction between neighboring spins. It quantifies how spin wave emerges depend on the wave vectors. This dispersion indicates that uniform processions mode when k equal to 0. This k is nothing but the wave vector associated with the spin wave is nothing but magnon. The term dk square is the contributions from the exchange interaction and represent the energy cost of facial variation in the spin structures. Okay, so this physical interpretations implies uniform procession mode when k equal to 0. The frequency is purely determined by the Zeeman terms. Okay, gamma h, representing a uniform procession of the magnetization in the applied magnetic field. On magnon depressions, for suppose k equal to non-zero, okay, k equal to non-zero, the term dk square comes into play, which increases the frequency. K is non-zero, which increases the frequency, which indicates that the shorter wavelength magnons have higher energies due to the exchange in interactions. And the decay square term captures how difficult it is to induce variation in the magnetizations over short distances. A higher d value implies a. So here, this depressions indicates that shorter wavelength magnons have higher energy due to the exchange infections. Okay. So this depressions is giving that much applications helps this dispersion relations helps the characteristics of magnon dynamics under Terahertz radiations, going field in spintronics for ultra fast information transfer and magnetic resonance to understanding ferromagnetic resonance and mahonic band structures. It's used in designing magnetic crystals and wavegates for potential applications, spin-based logic and memory devices. Okay, memory devices. So this one we can based upon that yes, alpha omega. Here alpha omega equal to 1 by m imagery of this say omega, it is used to describe absorption Terahertz radiation by a system. So alpha omega absorption coefficient as a function of frequency omega, and this one is angular frequency of Terahertz radiations, and this imaginary part of susceptibility. So this absorption coefficient represent the amount of energy absorbed per unit length at Terahertz radiation propagates through a medium. It depends on the interaction between the electromagnetic field and the material excitation. Okay, magnetism or phonons. See, see this concept. Students are there. We are giving that lectures. What are the concept is understanding, and how much he understand, and how much information he is getting. That is the concept. Okay, so here also this absorption ratio, the amount of energy absorbed per unit length at Terahertz radiations propagate through a medium. It depends on the interaction between the electromagnetic field and the material's excitations. Okay, and susceptibility. The susceptibilities describes how much this one susceptibilities. Material response to an applied electromagnetic field. In general, it has both a real part and imaginary. How that material responds? If you are asking questions, okay, asking questions to the students, how he responds. Okay, how he responds. Okay, even though he is not knowing that concept, but how efficiently he address the questions. Okay, how material responds to the questions that is raised by the staff members. Okay, so this one indicates how a material responds to an applied electromagnetic fields in general, and represents this one real part and image, but real part generally represent the material's ability to store energy. Okay, dispersions. Okay, real part means dispersions and imaginary part means absorption. Okay, represent the material ability to absorb energy. Imaginary part means absorbs energy. Real part means store that energy. In the context of Terahertz radiation, the imaginary part is responsible for converting electromagnetic energy into internal excitation, such as phonons or magnetic, leading to absorptions. Okay, and frequency dependence. The term 1 by omega accounts for the frequency dependence nature of the absorption in many physical systems. For lower frequencies, absorption is typically stronger because low energy excitations like magnetism or acoustic phonons are easier to excite. The magnon systems is related to spin susceptibilities, that application of magnons or phonons which measure the material response. What are the material response of that magnetic field? Okay, so in phonon system represent that lattice vibration induced by the Terahertz fields, that vibrations. Okay, lattice vibration, and these expressions quantifies how much energy is absorbed in Terahertz radiation interact with the systems depending on the strength of the system response given by this susceptibility. Okay, susceptibility. So these all equations explaining that absorption capacities and vibrations and that materials response. So that's why we are studying about that that's elementary excitations. Okay, why that study that Terahertz radiations and elementary excitation in the modern science. Okay, that's why we are studying. So next one is hexagon. Next one is hexagon. Is it audible? Is it audible?
Yes, sir, it's audible.
Okay, okay. What is the time, madam? Time half hour more or
Until 4:30.
until okay. Now in between 10 minutes break, madam. Or
Yes,
otherwise
sir.
continuously we
Yes,
can
sir,
take.
we can have a small break, sir.
Okay, okay. Up to 4:30, isn't it?
Yes, sir.
4:30. Okay, 4:30. Now 3. 3:30 we can take after the 10 minutes break after.
Okay, sir.
Okay, okay. 3:30 half an hour I can take. So here exciton. And exciton is a bound state of an electron and a hole. Okay, see there magnetron that spin waves we are seeing here. An exciton is a bound state of an electron and a hole. Okay, hole. That is an absence of an electron in a semiconductor or insulator. Excitrons play a significant role in optical absorption and emission in semiconductors. Okay, excitrons plays an important role in optical absorption and emission in a semiconductor. So this exciton have a major role in the development of optoelectronic and nanomaterial-based technologies, and exciton plays a critical role in light absorption and charge separation in organic photovoltaics. And excitrons are responsible for light emission in organic LEDs and quantum dot LEDs. These are being studied for potential application in low power electronic devices. So exciton's recombination improves the sensitivity of photodetector in various optoelectronic applications. Okay, so exitons and Terahertz radiation. Exitons and Terahertz radiations. Here also we are studying about the elementary equations. This exiton bound electron hole pairs. Here mainly we are focusing on bound electron hole pairs can couple with Terahertz radiations, altering their binding energy and transition frequencies. So this is the exciton binding energy. eh? EB equal to e power 4 m or 2h square epsilon square. Here where E is the electron charge, m or is the reduced mass of the exciton, h is the reduced Planck constant, and epsilon is the dielectric constant. Okay, this is the binding energy state, and this Terahertz exciton polarization. This exciton polarization under Terahertz fields is described by this one. Omega because is the dipole moment. Okay, dipole moment because electron hole pass. Okay, dipole moment. Omega naught is the exciton resonant frequency, and gamma is the damping constant. So these all terms explaining here. The frequency P omega is the frequency dependent polarization induced in the material due to the applied electric field. Due to the applied electric field, mu, the dielectric dipole moment, is the electric dipole moment associated with the excitonic transition, which measures how strongly the excitation interact with the external electric field, and E omega applied electric field as a function of frequency, and omega naught the response frequency of the exciton, typically corresponding to the energy difference between the electron hole pairs bound state and the ground state. Okay, bound and ground state. And gamma, the damping factor, are line with representing the broadening of the exciton resonance due to factors like radiative decay and non-radiative recombinations or interactions with the lattice. Okay, material. So I gamma omega, a complex term representing energy dissipations. Okay, the imaginary component accounts for losses in the system leading to absorptions at the resonant frequency. From this terahertz exciton polarization and exciton binding energy. Okay, so what the physical interpretations we are happening now? The denominators, this one, omega naught square minus omega naught I gamma omega resembles the response of a damped harmonic oscillators. This is analogy is often used for excitons because they behave like oscillators bound by a Coulomb interactions. Coulomb interactions. Okay, charges interactions. Okay, the resonance when the applied frequency omega approaches the resonant frequency omega naught, the polarization is enhanced, leading to strong absorptions or scattering. That is because we are utilizing the terahertz absorptions that is scattering and reflection properties. Okay, this is a scattering and reflection properties. So here the polarization is enhancing that, leading to strong absorptions or scattering property of the electromagnetic wave. This behavior is characteristic of exotonic absorption. Okay, so what is the need for coach? What is the need for the teachers? What he can expect from the students? Okay, that coach is seeing that whether that person is having a high potential in that for cricket coach. For example, you can take a cricket coach. He can extract that information by that integral fellow uh, um, fellow characters and how he performs on the ground, whether he can eligible to bowl or whether he is more confident in the batting or he is eligible for fielding or keeping. He is judging, no. So by analyzing easily we can use that fellow for any category. Okay, any application. So like this here we are analyzing the behavior of characteristics of external observations speaks. Okay, and the term I, gamma, omega broadens the resonance, reducing the sharpness of the observation peak. Higher damping implies shorter exciton lifetimes or stronger interaction with the environment. The exciton's application, optical absorptions. This uh, this equations. Okay, exciton polarizations stations used to describe exciton absorptions in materials. Absorption materials. So by seeing that mark sheet, we can say this fellow is good student. Okay. Uh, by the grade sheet, seeing the grade sheet, we can identify he is in good in this subjects. 10 subjects are there, I scored some good marks in subject, he is at least in that subject. We can easily come to conclusions. Okay. So, excitonic absorption material, especially in semiconductors, where exciton resonance play a vital role in important role in the optical properties and photoilluminance. The behavior of P omega helps model exciton emission spectra when excited by external light. Okay. And terahertz spectroscopy. This terahertz radiation can probe exciton dynamics, providing insight into exitonic binding energy and light patterns. Okay. And quantum well and 2D materials, exciton in quantum well and 2D material like monolayer MOS to exhibit pronounced exciton resonance that follow the type of dispersions behavior. That coming to this polaron. Okay, next one is polaron. Um, Here, this we know that actually photonic and quantum technologies, plasmonic and exciton effects are crucial for designing and quantum dots, single photon emitters, and photonic chips. So, so before that, here you see the this by knowing this exciton, polaron, exciton, yes, uh, exciton. See here. Why we are studying that elementary excitation? Huh? Elementary excitation. See here that the plasmonic and the exotonic effects are crucial for designing quantum dots, single photon emitters, and photonic chips. We are analyzing them, easy to represent this. We are knowing that elementary excitation. So elementary excitation would be like that only. See, uh, sometimes, somewhere we have to follow the protocol. Okay, in a house we can sit anywhere and we can sleep anywhere. Okay, bedrooms also there, bedroom also there, but we can sleep in that hall also while watching that TV that and all. But in the puja like room or some places we have to follow the protocol. Okay, so by knowing that elementary exhibition in materials, we can know. Okay, we can easily identify that characteristics. Okay, characteristics. Hmm. So that's why we are studying about this things and Polaron. Polaron. A polaron is a quasi-particle consisting of electron, okay, or hole. Anything, electron or a hole, okay, electron or a hole. Here, that is coupled with a deformation of the surrounding crystal lattice due to its electric field. Polarons are essential in understanding charge transport in material with strong electron-phonon interactions. Okay, polaron is a quasi-particle consists of electron or hole. Okay, that is coupled with a deconformation. Is it audible? Slides are visible?
Yes, sir, it's audible, sir.
Okay. Pronouns are essential in understanding charge transport in materials with strong electron lattice interactions, and it is important in understanding charge transport in materials like lithium-ion batteries. And transport underpins charge mobility in organic materials used for organic photovoltaics and flexible electronics, which are relevant for understanding that the structure, electron and lattice interaction in some unconventional superconductors. And Polaron affect the thermoelectric properties of materials, influencing their performance in converting heat to electricity. Okay, heat to electricity because the energy transport and superconductivity phonon interactions heat transport and play a crucial role in unconventional superconductivities. Okay, so photon and terahertz radiations. Photons, electron phonon coupled states interact with terahertz radiation due to their phonon induced mass. Photon binding energy. This is a photon binding energy. Alpha H omega naught. Here, this is alpha is the electron phonon coupling constant. Omega naught is the phonon frequencies. Here m star, that is effective mass of polaron, m star equal to n e 1 plus alpha over 6 m here bare electron mass. Terahertz conductivity represent sigma omega sigma naught 1 plus I omega tau p. Here tau p is the polaron relaxation time, and sigma naught is the DC conductivities. Here sigma omega, the complex electrical conductivity as a function of angular frequency omega. Sigma naught conductivity of the material, which represents the material intrinsic ability to conduct electricity and a static electric field. Okay, omega angular frequencies of the applied electric field of electromagnetic wave. Omega we know the 2 by f. Tau p, the relaxation time of charge carriers, which represent the average time between collisions or scattering events that disturb the carrier motions. Okay, I omega 2p. This term representing the representative response of the carrier to an alternating field, and the imaginary component indicates phase lag or energy. Generally, that imaginary component indicates the energy dissipations. The physical interpretations at low frequencies, omega very less than 1 by tau p, the conductivity is approximately sigma naught. The material behaves as it would under DC conditions. This frequency is to be. This means this relaxation time of charge carrier. Tau b indicates the relaxation time of charge carriers. Uh, Average time between the collisions or scattering event that disturb the carrier motions. Okay, this one omega tau p is less than omega na. It would under DC condition. If omega greater than 1 by tau p na, the carriers cannot follow the rapid changes in the field, leading to decreased conductions. Very greater na decreased conductions, less than indicates that under DC condition. But complex conductivities, the conductivity has both the real part and an imaginary part. That is, the real part is nothing but dissipative representing energy, and imaginary part which indicates reactive representing energy storage in the system. Okay, reactive na storage in the system. Uh, Real dissipative means representing energy losses. Okay, the imaginary part is critical for understanding reflectivities and directive behavior. So where that the main application focuses means terahertz and optical conductivities. This is widely used to model conductivity in material, semiconductors, plasma and terahertz frequencies. And system where platforms are excited, this equation describes the frequency-dependent response of free electrons to electromagnetic waves. So that all materials, these elementary excitations, this give that details pictures. We are taking that master health checkup now. It gives that is a BP level, sugar level, our kidney functioning, heart functioning, everything we can know. No? So like this here, we have to study about that there are serious elementary exaggerations, how the things are going on, and easily we can come to conclusions. Okay. So important for understanding how materials absorb, reflect, or transmit terahertz are optical radiations and dielectric functions, which indicates related to the dielectric function epsilon omega by epsilon omega, which governs the material is response to the electric fields. And terahertz spectroscopies and elementary excitations. Okay, terahertz spectroscopy and elementary excitations. Actually, terahertz spectroscopy applications. Terahertz spectroscopy application mainly. Terahertz pulses can directly excite and probe elementary excitation, offering a new window into quantum phase transition and ultra-fast dynamics. Okay, ultra-fast dynamics. Because the use of terahertz pulses for quantum computing, ultra-fast switching, and coherent control of qubits, and terahertz communication for what are the ultra-fast and secure wireless technologies. And we can use it. We can use it. Okay. So the phonon modes, probing phonon modes, plasmonic behavior, exidons and terahertz radiation, Magellan studies. This one indicates implies a terahertz observation can be used to identify specific phonon frequencies and lattice structures. See, specific phonon frequencies and lattice structures used for detecting transitions, ferroelectric to paraelectric transitions, ferroelectric to paraelectric transitions. This plasmonic behavior is study of surface plasmons are critical for enhancing sensor and material materials. And understanding plasmon dispersions is essential for Terahertz communication systems. Understanding. See, before going to play in that match, we have to know about that opposite fellow pros and cons. Okay, then only based upon so we can see that pitch condition also. Pitch who is bowling. If you are going to bat in the ground now, we have to know the pitch condition and opposite who is bowling, that is spin, fast bowling. You have to know the characters. Like this, here we are analyzing. Okay, so the Terahertz observation reveals exotonic states and semiconductor and perovskites materials essential for solar cells and light emitting diode applications. Magnum studies Terahertz spectroscopy solves for time-resolved studies of spin dynamics advantage the field of spintronics. Okay, and terahertz radiation and Ponon's lattice vibrations. Ponon's lattice vibrations. In crystalline solids, terahertz radiation can excite optical phonons, which are collective lattice vibration involving atoms oscillating out of phase. See, by this radiation and the lattice vibrations, we can know the material characteristics. Terahertz spectroscopy is used to probe phonon modes, helping identify structural and vibrational properties of the materials like semiconductors and ceramics. Okay, and thermal transport. By studying phonon behavior, scientists can design materials with tailored thermal conductivity useful for thermoelectric devices. That's why we are studying about that elementary exhibitions. Okay. Practical insight. Phonons are vibration of atoms in a solid. Think of them as a sound waves traveling through a crystals. When terahertz will hit a material, they can shake the atoms and create these vibrations. So terahertz radiation is used to study how heat travels in material. Okay, thermal conductivity, which is known as thermal conductivity, which helps us design better thermoelectric devices, convert heat into electricity. So by we can real-time example we can say this material quality testing. Terahertz pulses can detect defects in semiconductors by observing how phonon vibration change when the heat cracks or impurities. Okay. So this one is phonon lattice vibration. We can know it is mathematically uh, descriptions. Quantized vibration of atom in a crystal lattice. So energy equal to h omega. Omega is the angular frequency of the lattice vibration. Carry heat and mediate sound in the solid. And here spin wave descriptions. Magnons. Phonons lattice vibrations. Magnons indicate spin waves. Collective excitation of electron spins in magnetic material E equal to h omega k. Here C is a spin wave. Here spin wave for wave vector k. Wave vector k. Okay. describe the dynamic behavior of magnetic ordering and can be used to study magnetic material. So we can study by using that magnetic material. And Terahertz radiation and magnons are nothing but spin wave. Terahertz pulses can excite magnons in magnetic materials such as lithium, iron, garnet, where we can use control over spin waves, paving the way for faster and energy efficient controlling devices. Magnetic data storage, understanding magnon dynamic aids to developing next generation magnetic memories and logic devices. Practical insight could be that like waves of aligned springs in a magnetic materials and Terahertz radiation is applied, it can excite or change these spin waves. So Terahertz pulse can flip or manipulate spins in magnetic materials, which allows control over magnetism without touching the materials. That applications we can easily get it. Magnon control can lead to new type of magnetic memory devices, fast and more energetic in that 6G. This is a terahertz radiation and magnon spin waves. Okay, magnon represent the collective spin wave exiting in magnetar material. The interaction between magnetons with an external terahertz magneton field can be described by the LNG equations. dm by dt equal to minus gamma m into h efficiency. This thing. This one m is the magnetization vector. Gamma is the biometric ratio. This one H evidence is the effective magnetic field, which can include terahertz radiations, and alpha is the damping factors. So this dispersion relations. So the dispersion relation is giving the character of that waves. So the ferromagnetic material here omega k equal to psi H gamma H is the Z1 interaction with the external magnetic field. So D is the stiffness constant. So terahertz radiation and plasmons, electron oscillations. Metal nanostructures and the graphene exhibit plasmons resonance when interacting with terahertz radiations. Plasmonic sensors can enhance the sensitivity of biosensor useful for detecting biomolecules. Okay, this plasmons detecting biomolecules. And metamaterial terahertz radiation is used in developing negative index metamaterial for tracking devices and advanced lenses. Okay, so here see terahertz radiation plasmons electron oscillations. The collective oscillations of free electrons plasmons in materials are described in the plasmon frequency omega p equal to here. N is the electron density, E is the charge of electron, epsilon naught is the limit of free phase, this is the mass of the electron. So here terahertz waves with frequency interact with the material. The dielectric function is modeled as here. Epsilon bit is high frequency dielectric constant. This omega p, omega k. Okay. See this one. This is the plasmon frequency. This is the plasmon frequency. Okay. This is the total frequencies. So terahertz radiation and excitons, electron hole pairs, like gallium arsenide, the terahertz radiation can manipulate exciton and dynamics. Mostly they are using that gallium arsenide is good semiconductors. So mostly they are using that gallium arsenide. Applications we can use that study of excitons help improve the efficiency of solar cells and lasers. And excitons manipulation is key in quantum computing and quantum communication technologies. So and excitons, electron hole pairs. This one, this excitons model is in the hydrogenic model. So here m is the reduced mass of the electron hole pair, and epsilon is the relative dielectric constant. N is the principal quantum number of excitation, and this is the terahertz radiation applied exciton transition between energy level and leading to observation peaks of specific frequency corresponding this one. This equation Delhi. Okay, Delhi. And terahertz radiation photonons, that is electron phonon interactions. Terahertz pulses reveal polarization formula and dynamics, superconductivity and energy materials. Studying photonons helps understand high temperature and their conductivities, and insight into electron phonon coupling in designing better materials for energy energy storage and conservation. Terahertz radiation and polarization (LMC). In material like perovskites, terahertz radiation can create exciton polarization, hybrid light matter states, quantum light source. Exciton polarization can be harnessed for generating coherent light with low energy loss. Okay, and Bose-Einstein constraints driven polaritons are used to create room temperatures which have potential in quantum technologies. This is a light matter coupling. Okay, light matter coupling. Photons are a hybrid particle formed by coupling terahertz photons to excitons or phonons. This is a Hamiltonian for polaritons. The omega c, the cavity photon frequency, omega x is exciton frequency. This one is photon operators, A star and A plus and A B. B plus B is the exciton operators. G is the coupling constant. The coupled system leads to two polariton branches with frequencies. These are studies using spectroscopy to control light matters interaction. Okay, how we can control the light matters. The electron oscillations, terahertz radiation plasmons, practical insight. Imagine electrons in a metal behaving like a fluid. Okay, electrons behaving like a fluid when hit by terahertz. When terahertz hit and the metal, the electron in a metal behaving like fluid. So this electron oscillates collectively creating plasmon waves. The nanomaterial like graphene plasmon accelerators helps enhance electrical conductivity and control light at very small scales. So we can use these plasmons enhance the direction of biomolecules like proteins or viruses and biosensors, which used in medical diagnosis, medical purpose and environmental monitoring. And terahertz radiation and exciton electron hole pairs. Is it audible?
Yes, sir, it's audible.
Ah, okay, okay. Uh, Practical insight: in semiconductors, when an electron absorbs light and jumps to a higher energy level, it leaves behind a hole. This electron hole for a pair is called an exciton. We know that terahertz can manipulate these pairs, can measure how tightly excitons are bound, which is critical for entering solar cells and LEDs. We can use by controlling exitons with terahertz pulses, we can make more efficient light emitting diodes and the sensors. Okay, these are the electron hole pairs equations already just previously discussed. Okay, and the terahertz radiation tolerance, electron phonon coupling, practical insight. Sometimes an electron moving through a material tracks nearby atoms along with it. The clump of an electron that is open distance is called a photon. Okay, terahertz can reveal the motion behavior of photon. Terahertz waves, okay, it is used to reveal the motion and behavior of photons. So it is used to study how photons behave in battery materials or high temperature superconductors. By understanding electron-photon interaction, we can design better batteries. We can easily design the better batteries and superconductors. Okay, this is the electron phonon coupling model. Previous slide we had seen it, and this one light matter coupling, terahertz radiation polaritons. Polaritons are hybrid particles that form when terahertz light couples with excitons or bonds in a material. They combine light and matter properties, allowing control over both. So the light can create polaritons, which are used to generate coherent light. So this one is to create room temperature, Bose and condensed state, a matter state of matter, a state of matter useful for quantum computing. This one, electron phonon coupling. Electrons are holes that interact strongly with lattice vibration, becoming dressed with a cloud of photons. Energy of polaron E naught by E self energy. So here that self energy accounts for the interaction between the particles and lattice, found in ionic and polar materials affecting conductivity and mobility. Polarization on light matter coupling, formed by the strong coupling of photons with excitons or phonons. this relation, dispersions relations, cavity photon frequencies, exciton frequency, and G is the coupling strength. The study in optoelectronics and photonics to understand light matter interactions. So the general application of these spectroscopies, non-destructive testing, can penetrate many materials without damaging them, making it ideal for scanning electronics on or artworks and security scanning used in airport body scanners because it can detect hidden objects without harmful radiations. That is, without harmful radiations, and privacy also could be there. And biological imaging, Terahertz pulses can reveal the water content in tissues used for detecting tumors in medical imaging, through directions. And elementary exudations are the smallest quantized disturbances or collective motions that occur in a material system, representing the dynamic behavior of its particles. They are analogies to particles, but are not individual physical entities. Instead, they describe collective or quantized energy state in condensed matter systems. Okay, this is elementary exudations, smallest quantized disturbances. Okay. Terahertz radiation and phonons vibrations. We have seen this. Phonons are vibration atom in a solid. Think of them, sound waves traveling through the crystals. This one already we have discussed here. Okay. When terahertz waves hit in a material, they can shake the atoms and create that vibrations. So, how that heat travels in materials? So this material quality testing, terahertz pulses can detect defects in semiconductors by observing how phonon vibrations change when they hit or impurities. So this one, lattice vibrations. Phonon atoms lattice vibration crystals. The vibrations of atom can be modeled using harmonic oscillator equations. M d square u by dt square equal to minus t. M is the mass of vibration atom, and k is the spring constant. Q is the displacement equilibrium. So dispersion's relation between frequency and wave vectors. Omega k is the frequency of the phonon or wave vector, and A is the lattice constant. When terahertz electromagnetic field E of t interacts with optical phonons, which shift the frequency, which can be measured through terahertz observation spectroscopy. And the spin waves, it can exit or change the spin waves. Terahertz pulses can flip or manipulate spin in magnetic materials, allowing control over magnetism without touching the materials. You can use for data storage. And this equation we have seen it, I think. Terahertz radiation plus one also previously we had discussed. Radiation exidons. This is repeated slides. Okay. Yes. Yes. So we have discussed about the terahertz radiations and the elementary exudations. What is the history and needs? Because terahertz radiation refer to electromagnetic fields in the frequency range, and elementary exudations refer to particles and collective modes in condensed matter systems that describe fundamental interactions such as phonons, magnons, plasmons, and exudations. This thing we have discussed. These exudations play a crucial role in understanding quantum materials, superconductors, and nanotechnologies. And history of terahertz radiation and elementary exudation we had seen it. And the historical development of elementary exudations we had discussed. And what is the need for terahertz radiation and elementary exudation in modern sciences? The need, why we are studying the terahertz radiations, because of that non-ionizing, safe for imaging. Unlike X-rays, terahertz waves do not ionize biological tissues, and making them ideal for biomedical imaging and security scanning. And it is useful in chemical sensing and paramedicals, and it enabling terahertz per second in that wireless communication, data transfer, and it reveals carrier dynamics in semiconductors, superconductors, and quantum materials, and it gives that application of to help in studying cosmic background radiation, interstellar molecules, and plasmomatics. and study of elementary radiations. Impulses determine the fundamental properties of topological insulators, high superconductors and 2D materials, and low power computing and memory devices, yeah, and heat transport and play a crucial role in unconventional superconductivities. And Terahertz funds can directly excite and probe elementary excitation, offering a new window into quantum-based transition and ultra-dynamic physics. So, this radiation and elementary excitations are at the frontier of modern physics and technology. These applications span wireless communications, quantum material, bioimaging, and ultrafast science. With rapid advancement in terahertz generation, detection, and AI-driven analysis, these fields will revolutionize next generation computing, materials engineering, and biomedical diagnostics. Okay, so elementary excitations are the small quantities disturbance or tight motion which occurs in the material system, representing the dynamic behaviors particles. Okay, so it plays that important roles in study of this elementary extension, playing that important role in Terahertz communication systems. So with this, I conclude my first sections. If you have any questions, you can ask. Otherwise, we can give 10 minutes break. After that, we can start uh, next sections, source and directors. Is it audible? Is it
Yes,
audible?
yes, sir. It's audible, sir.
Uh-huh. Any queries? Yes, we can give 10 minutes break. After that, we can start.
Yes, sir. Sure, sir.
Okay. 3:50 we can start. 3:50 we
Okay,
can
sir.
start. 4:50 we can end. Okay.
Sure, sir.
Okay. Thank you.
Okay, sir.